I am absolutely delighted to introduce today's speaker, or today's colloquium speaker, Erin. Erin was a Gates Scholar here for her master's and PhD at the IOA before moving back to the US for a Hubble Fellowship at the University of Maryland and in 2015. And from there she moved to MIT as an assistant professor. The slightly embarrassing thing is that I didn't know any of this when I first invited her here. It was only when she said, "Oh, I love my time in Cambridge," well, I realized that, oops, she'd been here before. But she came onto my radar when, among a long list of prizes, she was awarded the Newton-Lacey Pierce Prize by the AAS in 2022. And that was specifically for outstanding achievements in observational astronomy. And I think she will tell us a bit more about that today. Thank you very much, Erin.
All right, thank you. Thank you, Elme, and thank you everyone for coming today. It really is like a special honor and excitement to be invited back to your PhD institution to give a talk. So it's really been wonderful to be here this past week, and I'm excited to tell you a little bit about the work that I've been doing since my time at the IOA. So I'm going to be telling you a little bit about black hole accretion in the TDAMM era, and I learned this week that this acronym TDAMM is not as popular here as it appears to be in the US. Right now this is like a buzzword. It means time domain and multi-messenger astrophysics. The decadal survey kind of highlighted time domain and multi-messenger astrophysics as one of the key priority areas of the next decade, and this buzzword TDAMM has been going around. It's kind of an annoying acronym actually, so I'm glad that it actually hasn't taken on here. Maybe Robin was going to try and come up with a better phrase for it. But you know, by and large, what I'd like to tell you a little bit about today is how we're studying black hole accretion and supermassive black hole growth using time domain techniques, and hopefully we're making predictions for multi-messenger events that we could see in the future. So just as starting with a little means of motivation, I think like for me, one of the first images that really got me excited about astrophysics was the Hubble Deep Field images. And now we have even, better images with the James Webb Space Telescope, and we're seeing, images like this where we can see, the universe is just, even in a small snapshot like this, we're seeing local galaxies where you can even resolve the beautiful structure, and we're even seeing, redshift 14 galaxies, and even quasars Roberto is finding at a redshift of 11. And what blew me away when I first saw an image like this was also to learn that at the center of each one of these massive galaxies is a supermassive black hole sitting at the center. That's 1 million to 1 billion times the mass of the sun, and typically like 1,000 times less massive than the galaxy in which it resides. And the question, still the ongoing question, is how do you get a black hole that big in the first place? And how is it that at redshift of 11, when the universe was just a few 100 million years old, how are we still seeing, black holes that are over, 1 million, 10 million times the mass of the sun? How did they grow so fast? How did they grow so quickly? And how do they evolve over cosmic time? So we know that a lot of that growth is via the accretion of gas onto the supermassive black hole, and also through mergers of black hole systems. But this accretion process is not quiet. It's not just quietly growing the black hole. We also know that accretion releases tons of energy as well back into the system. And so as it turns out that these accreting supermassive black holes can be some of the some of the most luminous objects in the universe, completely outshining all of the stars in the galaxy. And we can also see things like I heard about, I know you heard from last week. Julie gave a beautiful colloquium on, I'm sure a beautiful colloquium on clusters of galaxies, where you can see even like this brightest cluster galaxy producing these radio jets that you can map out via synchrotron radiation in the radio, punching out hot gas, carving out these bubbles in hot gas. So you can see this central black hole is affecting much, much larger scales. And so the question that I'm very interested in, is that we know that this feedback process is important for understanding, the coevolution of the growth of the black hole and the galaxy at large. And the question that I have is, how do you produce all of this radiation, and how do you launch these relativistic jets? How does this accretion process that's growing the black hole then eventually lead to the launching of these jets and so forth? And so if we want to understand, this intersection between accretion and ejection, inflow and outflow, and we want to understand how all of that energy is released, we need to zoom into the innermost regions, because that's where most of the energy is being released within 20 gravitational radii or so, or even smaller regions if that black hole is maximally rotating. And so a lot of my work is trying to understand, what does it look like in these close environments around black holes? How do we go from accretion of matter and to the launching of these jets and the radiation that we observe? So what we're trying to do is zoom into the innermost regions, and we want to measure things like, for instance, the spin of the black hole. This is not only just a fundamental parameter that describes the black hole itself, but also astrophysically extremely important. So the black hole spin will, if you have, just as a reminder, if you have an accretion disk around a non-rotating black hole, you'll form, your innermost stable circular orbit will be at 6 gravitational radii. And if you spin that black hole up, frame dragging will support more orbits closer to the black hole, and so that innermost stable circular orbit moves into 1RG. And you can imagine that this will change your radiative efficiency of this accretion process. Kind of determines how much material is accreting onto the black hole versus how much is being radiated away. And so understanding, the efficiency of accreting systems is, we want to understand the black hole spin to understand that better. Also, the black hole spin may be what's powering these relativistic jets that we see launching out from these central regions. And finally, last but not least, supermassive black hole spins can tell you something about the growth history of these black holes. So for instance, if we have, if we can map out, over all of the black holes in the local universe, and we can measure their spins with high precision, we can say, okay, well, we can look at the distribution of spins, and if they are more uniform, maybe that is telling us that these systems are largely grown from mergers where they have, different spin orientations, and you end up, the final product is something more uniform, whereas if these black holes are largely grown through the accretion of matter, via an accretion disk, you'll spin that black hole up over time, and you should see more of these rapidly spinning black holes. So, measuring the black hole spin not only is something that we're interested in studying these innermost regions for understanding how matter behaves in, strong gravity regime. There's astrophysical importance as well, helping us get back to these, big questions about how do black holes grow over time, and how do they, launch these jets and this incredible amount of radiation as well. So my approach to studying these accreting black hole systems is to use time variable and transient events to map out, to probe the causal connection between material that's inflowing through the disk and these and ejection, launching of outflows and so forth. And by time variable events, I mean, all of these systems we look with our telescope, so we want to look at these small scales around these accreting supermassive black holes, and all of them look like point sources, right? Even the Event Horizon Telescope, while Event Horizon Telescope is really great in very low accretion rate or quiescent black holes, the highly accreting systems, the actively growing black holes, look like point sources, are unresolved. And so can we use the time variability, the stochastic variability, and look for correlations to map out the accretion flow? And then also, and this will be the focus of my talk today, is kind of trying to probe this causal connection using extreme transients. And I'll focus on tidal disruption events, where we see stars getting ripped apart by black holes. They become maybe we see the fast accretion of matter, and then we can follow them up over time to see like the delayed, the late time launching of outflows and so forth. So that's kind of my general approach to studying these systems. And in particular, the sources that I'm interested in are active galactic nuclei, and this was really, I think, in my time in Cambridge was, my thesis was really laser focused on AGN, and while I still love AGN a lot, I've actually spent a lot of time right here in the Hoyle already talking about AGN, so I thought I would tell you a little bit more about some new things that I've been working on. And I also am excited about stellar mass black holes that are in companion systems with normal stars. And we're interested in studying the accretion flows in these systems kind of as like mini scaled down versions, micro versions of these AGN. AGN, we call these AGN for the impatient. But today what I'd like to tell you about really is focusing on these extreme transients, these tidal disruption events, and a new source of objects called quasi-periodic eruptions that are thought maybe to be the counterparts to extreme mass ratio in spirals, where you have a central supermassive black hole and a smaller scale orbiter around that system. And if there are any questions along the way, please stop and ask. Okay, so first, tidal disruption events. I probably don't have to give a review, as we have Martin Rees here, who really was the first to kind of think about the theoretical, propose the idea that these things should exist in 1988, and indeed, several years later, they were discovered. And now I would say it's become this like booming industry. So a tidal disruption event is where a star gets too close to a supermassive black hole, and the strong tidal forces of that black hole become so strong that they exceed the self-gravity of that star. And so the star gets ripped apart, and some of that, about half of that stellar debris, will accrete onto that black hole over timescales of several weeks to years. And so these TDEs are really important and promising for studying lots of different aspects of galaxies, nuclear star clusters, but also for understanding accretion as well. So some of the things that we're excited to use TDEs for, one is to probe quiescent populations of black holes, right? I've told you about the supermassive black hole systems. I've told you about stellar mass black hole systems. What about intermediate mass black holes? Where are they? And so perhaps, you could find, if they're not actively accreting, like all the time, maybe you could have the tidal disruption of a white dwarf around an intermediate mass black hole that was previously quiescent, and then it would shine bright, and we could follow it up. So detecting IMBHs, measuring black hole spin demographics in not just AGN systems, but also in a wider range of quiescent black holes as well. They're also unique environments for testing accretion. As I said, we can see, we know like roughly in these systems that it's accreting about half of a star. And we can watch, what happens after do you form a disk? And then how long after you've formed a disk do you form a jet or an X-ray corona, the hot plasma around the accretion flow? And can we, watch this transition from, different modes of accretion, very super Eddington accretion, and as the mass fallback rate or the accretion rate drops, you can see what changes, how does that accretion disk change over time? And whereas in AGN, you largely have to just do this by studying different populations of AGN, samples of AGN, in these TDEs, in principle, you can watch different modes of accretion just by staring at a single system. And then finally, and a little bit more speculative, I would say, is that there have been claims that these are indeed multi-messenger candidates, that they could be sites of high-energy neutrino emission. And I would say there's a big TBC next to that. What time will tell. Okay, so tidal disruption events. How do we find them and what do they look like? What we Martin and others early on came, with the prescription that you should see the mass fall. You can predict the mass fallback rate onto the black hole, and it should follow this stellar debris. Fallback rate towards the black hole should decay as t to the minus 5/3. Maybe you can see my pointer there. Time to the minus 5/3 power. And indeed, so early on, what we were looking for when we were looking for tidal disruption events are black holes, previously quiescent non-AGN systems that suddenly become very bright over timescales of maybe a month, and they decay with this characteristic t to the minus 5/3 behavior. And indeed, with these systems, these are all optically discovered systems now with large optical time domain surveys that are monitoring, many hundreds of thousands of galaxies. This is a signature that you've seen now in several systems. One of the other things that I think is kind of distinguishing, we want to be clear that we're actually finding tidal disruption events and not other kinds of systems. And one of the early ways of kind of distinguishing TDEs from AGN activity is that TDEs show a very soft thermal spectrum. And actually, Martin predicted that you should see a disk form and it would be, hot enough to produce, you'd see like the Veen tail, you'd see this, 10 to the 6 Kelvin black body emission in the soft X-ray band. And you can see now what I've plotted here is one TDE system in black there compared to AGN of similar masses in the local universe, all with different levels of different mass accretion rates, different levels of obscuration. But what's true about them all is that they show hard X-ray emission. Hard X-ray emission beyond the thermal disk emission. And this is from this AGN corona, this hot billion-degree plasma around the black hole that is really ubiquitous, or thought to be ubiquitous, in these accreting black hole systems. And these tidal disruption events do not seem to show them, especially at early times. At least this is like, when we see them near the peak, that seems to be a signature of these tidal disruption events. So these TDEs were, because we were looking for, we had predictions that they should be soft X-ray sources. Some of the early detections of TDEs were with the ROSAT All-Sky X-ray survey, and they were indeed looking for previously quiescent galaxies that became very bright soft X-ray emitters and decayed with this t to minus 5/3 power law dependence over time. So the first discoveries were made in the mid-90s, and now with the advent of optical time domain surveys, we're increasing our numbers a lot. I think there's roughly around 150 known TDEs to date. So some puzzles, some things that we know about TDEs and some puzzles. There's been a lot of work on understanding the theoretical rate, of how many TDEs you should expect in a galaxy per year, just from loss cone dynamics. And the theoretical rate is about 10 to the minus 4 per galaxy per year. So on average, a galaxy should have 1 TDE every 10,000 years. That's the predicted rate. But what we've observed is something quite a bit smaller than that. And so this is I think the current best estimate. And what we need to understand is is this related to some, observational bias, or is it telling us actually something, interesting about the stellar populations, for instance? We need to reconcile the observed versus the theoretical rates. And this is important because we want to use TDEs. We're moving into this demographics era where we're detecting a lot of these, and we want to understand, can we, for instance, use TDEs to measure black hole spin? This is like the mass function that we would, this power law dependence, but what you can do is compare that to, theoretical, different rates that you would expect for TDE populations. And what you see is that basically you should see, if you have a non-rotating black hole, you should have an upper, limit to the mass where you can get a tidal disruption event. And that's because at some point you get to larger and larger masses. The tidal disruption of radius is actually within the event horizon, within the innermost stable circular orbit of the black hole. And so you'll just swallow that black hole, swallow that star whole without it actually getting disrupted. But if you have, rapidly rotating black hole where the ISCO has moved in, then even in these high mass systems, you can have stars disrupting outside of the ISCO. And so if you had, a larger sample of highly rotating black holes, you should start to see these high mass TDEs. So these are, important reasons for, measuring, understanding well the rates and understanding our observational biases in the rates. Another puzzle that we've recognized in recent years is that TDEs live in very peculiar host galaxies. And this is kind of shown very nicely in this plot comparing the H-alpha equivalent width and emission versus the H-delta absorption. And what you can see, the gray points here are SDSS quasars. So you have your strong star-forming galaxies up here, and you have your red and dead galaxies down here. And the TDEs seem to live in this very unpopulated part of parameter space where you have not a lot of star formation, and in systems where your stellar light is dominated by A stars, and basically there's some starburst, post-starburst system where your O and B stars have evolved, but you're dominated by A-type stars. And this is like 0.2% of all of the galaxies. And yet TDEs seem to preferentially exist in this part of parameter space. And that's a very interesting puzzle, and I think actually was one of the reasons that people actually started to believe, like, oh, these are really something different. These are actually tidal disruption events. And the idea there's some physical ideas why you might expect TDEs to occur in post-starburst galaxies, or if these are like post-merger systems. Perhaps this merger would then lead to stars, more stars entering the lost cone of the black hole, and then you see more TDEs in those systems. But we also know that these systems are optically detected or soft X-ray detected, and perhaps there are selection effects. You're missing things in very dusty environments in these star-forming galaxies that can be very dusty. What are our selection effects? And so recently we thought that we could take on this problem, and this is thanks to work with Quichelet Day, who is an Einstein Fellow at MIT. Quichelet is an infrared astronomer. He's mostly working on the galactic plane, and of course in the mid-infrared is, you want to study, there's so much to do in the galactic plane. And what Quichelet did was to take the WISE all-sky mid-infrared survey and do difference imaging on the entire all-sky survey. So you can see like our science images, and you compare to a reference image, you take the difference, and you find transients, right? So Quichelet has been like a great collaborator and really interested in the galactic plane. And also, though, there's so many of these mid-infrared transients out of the plane, and this is how we started collaborating with Christos Panagiotou, my postdoc at MIT. And what we found kind of really early off the bat was this detection of a TDE candidate at 42 megaparsecs. So this is like the nearest TDE known to date, and it was right in our neighborhood, and yet we totally missed it in the optical, all upper limits in the optical, and yet it has this fast rise and t to the minus 5/3 decay, it's radiating a huge amount of energy, so it's not likely to be something like a supernova, and it's over a much longer baseline than what you'd expect from some very exotic supernova. We've done a lot of work to show that it has no previous AGN activity, and so we're very confident that this is indeed a tidal disruption event. And it just happens to be that, what we're seeing is the system is so dust obscured that you have massive amounts of extinction. That means that you won't see any emission radiated in the optical, but instead you're seeing the dust echo, the reprocessed emission in that dust, producing this strong mid-infrared flare. So now Megan Masterson, fourth year PhD student in our group, has taken this now to the next level and produced a sample of these mid-infrared selected tidal disruption events. And this is 18 sources. We're only doing this within 200 megaparsecs because just to start with some small number. And what this sample shows is basically more than doubling the rate of known tidal disruption events in the local universe. And basically you can compare, this is like the mid-infrared light curve here, and again, all of these have been non-detected in the optical, so missing in plain sight. And so with this large, doing this really detailed work to make sure that we really have no contamination from AGN or other interlopers, now Megan has showed that, comparing, the rates that we find in the mid-infrared to rates in the soft X-ray and optical, basically what we're finding is that we are almost nearly accounting for all of the missing TDEs, kind of getting close to this theoretically predicted rate of TDEs, which I think is encouraging if we want to use TDEs for instance, black hole spin demographics. And in addition, going back to this host galaxy plot, what we find is all of these are in star-forming galaxies. So none of these are found in post-starburst galaxies. And I think that that's not saying that it was, I still definitely believe that optically selected TDEs are preferentially happening in post-starburst galaxies, but they are also happening in star-forming galaxies as well. We just were missing these systems before. So I think that this work is encouraging, that it not only does it open us up to a wider population of black holes, but is kind of solving some of these big questions, big puzzles that we've seen in the field. We don't see any association with high energy neutrinos, for what that's worth. Okay, so now I'd like to move on with a few interesting case studies of tidal disruption events that are proving to be exciting puzzles. And some of this work is new as of a couple of months ago, and I would say we don't understand things completely, and I would love to hear feedback if you have any ideas. So let's start with this case of GSN 069. This was an X-ray discovered tidal disruption event candidate. Archival observations with ROSAT showed just on upper limits, and the XMM SLEW survey discovered this very bright 2-order of magnitude increase in soft X-ray flux and a decay over time. And back in, 2014, XMM took a pointed observation and the light curve looked boring, just like this. And in 2019, they looked again and we found these quasi-periodic eruptions. And this was something that was like totally unexpected. AGN we know to be stochastically variable. And this was like something that we had kind of associated with like, okay, there's some kind of more or less static disk. And these flares, who ordered that? Now, I think there are six QPE candidates discovered. Ricardo Arcodia did his PhD at MPE with the eROSITA team and is now at MIT with us. And he has now used eROSITA to discover 4 new QPE candidates. And this is what it looks like followed up with nicer observations. And what's very interesting about all of them is that they show this very soft X-ray spectrum, and very, no emission from a corona. So they don't look like they're strong AGN, at least. They really just have this thermal emission that gets, quite a bit hotter during the flare. So I first got into TDEs working with Johin Chakraborty, who was an undergrad student working with me for a summer, and now he's a PhD student at MIT. And what we thought was, okay, that was such a crazy surprise to find those flares in one of these sources. And have we missed any of these QPE sources? And so what we did with Johin was to use an algorithm that is used in the exoplanet community for quasi-periodic transits, dips. And what we thought was, what is a QPE but an upside down transit, and can we use this algorithm to search for more of these QPE candidates? And our search resulted in a lot of pulsars, of course, but filtering for things like that, we found this one candidate. And it shows, 1.5, maybe 2 flares. So it's still, not, it's only 2 flares. But it has very similar properties to the other QPE sources. And in the most exciting thing, I think, is that, we're confident that this is of the same source class because it was this, associated with a supermassive black hole. But unlike all of the AGN that show hard X-ray emission, this one, again, also only shows, thermal emission, soft X-rays. And what was most exciting was that when we realized that this source actually was observed because it was also a tidal disruption event candidate. And so here we have the second QPE associated with a tidal disruption event. And the QPEs were seen several years after the peak of the outburst. So I think so that second source was a good hint that there is this association of QPEs and tidal disruption events, these flares in tidal disruption events. And Thomas Wavers, who was he was here from recently as a postdoc in the Gaia group, had a very nice paper. And at the time we had 5 QPE candidates, and he showed that 2 of the 5 of these QPEs have host galaxies in these E+A post-starburst galaxies, like the optically and X-ray selected TDEs. So that was already an indication that the host galaxies are similar to TDEs. Unlike TDEs, when you put them on a BPT diagram measuring the narrow emission lines, they have some indications of narrow lines from an AGN. But no broadline region, intrinsically no broadline region. So the question now is, what are these systems? I think it's a pretty good, it's very clear now that at least some tidal disruption events can produce these very quasi-periodic flares. And the question now is, what is causing these? And I would say there are 2, definitely now we have 6 QPEs. There are 60 theory papers coming out with ideas for what's producing these flares. But they generally break down into 2 classes of models. One where you have some kind of disk instability, maybe disk tearing, and you're seeing some kind of precession effects there, some radiation pressure instability. And I think that these models have become more and more popular in recent years, Emery-based models where you have a supermassive black hole and a stellar mass orbiter. This is just one example of a nice paper that I like the title of, is literally Emery extreme mass ratio in spiral plus TDE equals QPE, and just very clear and says it all in the title. And the idea with these models is, let's say you have a star or a stellar mass black hole, and you have an accretion disk that's formed perhaps from the tidal disruption event or from some pre-existing AGN. activity. And you're seeing that this, on every orbit, twice every orbit, the star is interacting with the disk and causing these flares, quasi-periodic flares. So I would say what's nice about the Emery models, or these orbiter models, is that they can make predictions. And one of the ways that I think, reasons that people have gotten really excited about it are observations like this in GSN 069, where you see these are quasi-periodic flares. So you see like a short recurrence time followed by a long recurrence, short, long. And in an orbiter model where you have some object that's orbiting at, like 100 RG or something that's on a mildly elliptical orbit, right? Maybe you have, the longer recurrence time here, followed by shorter, because of the ellipticity of the system. And so that was kind of nice, that's a nice prediction from the Emery models. But then you have systems like this one called ERO-QPE-1 that Ricardo discovered with ERO-Zeta, and he and Johin and our team have been using NICER to follow this guy up for 3.5 years. And what we find is that this is like the troublemaker object. It doesn't do this nice long, short behavior. It kind of is all over the place. And this was, I think, very tough for some of these Emery models that you should expect kind of more or less periodic emission as the orbiter goes around. So Johin did some really nice work on timing of the QPEs. And this is a little bit busy, but what he did was, lining up these flares and looking for their subsequent flares and trying to measure, okay, what do I expect the period to be and what do I actually measure the period to be? So he made what we call these O minus C, observed minus calculated timing residuals, made famous by, the measurements of the Hulse-Taylor pulsar, right, that they were able to measure, use this to measure gravitational wave in spiral. And what Johin found was that, we expected there to be a period of around, a day or so. But what he found was that the timing of the arrival time of these flares seems to be modulated on a 6-day period, or roughly 6-day period. So, and it works very well in some cases and maybe not so well in others. So, take it with a grain of salt. But it looks like there is some structure to when the arrival time of these flares. And in fact, this had been predicted in Franchini et al. That if you include things like the nodal precession of the underlying disk, that at some parts in that, if you have this orbiter that's crashing into your accretion disk, at sometimes in the precession, this 6-day cycle, you'll be catching that, you'll be intercepting the compact object earlier, and then at other times you'll be catching it later. And so perhaps this, this timing modulation that you're seeing can actually be, something that we predict, and time will tell to see if things like this will, if we can continue to time these systems well, including things like precession effects. But I think that it is promising that, what I like about these Emery-based models, I'm not willing to bet my house that it's an orbiter causing these flares, but what I do like is that you can make predictions and test them with long-term monitoring. So in the last, I don't know how I'm doing for time, little bit, I want to tell you, my watch just died, unfortunately, but tell me when I should just wave me down. Okay, great. In the last 10 minutes, I'd like to tell you about this AGN called 1ES 1927, which has been like one of the most fun AGN that I've ever gotten to work on. And I'll tell you a little bit about the story of this source, and we think that it's a TDE in an AGN accretion disk, and some exciting new revelations as of a couple months ago. So this is 1ES 1927. It was a known AGN system, but in 2018, we found it with the Assassin All Sky survey in the optical, and it had this fast rise and this suspiciously T to the -5/3 decay over time. Since it was an AGN, we were, kind of, hesitant to call it a tidal disruption event, but I think, given its other properties, I think it looks like a good case for a tidal disruption event occurring in a known AGN disk. So what was exciting to me about this source was that it had really beautiful archival observations pre-outburst, which is unusual. It's so nearby, it's like 80 megaparsecs, and had been looked at with XMM Newton in the X-rays. And it kind of looked like a typical type 1 AGN, where you see, again, this hard X-ray emission, little absorption, just hard X-ray emission from that X-ray corona. And then after we saw the outburst in the optical, we followed it up with NICER and with XMM Newton. And what we discovered was the source looked totally different. The hard X-rays had completely disappeared by 2 orders of magnitude or more. And all that we were left with was this thermal black body, accretion disk spectrum. And we were monitoring this source then with NICER for several, months, and we saw it slowly decay again with the optical over time, and we were like, that was fine, and we started getting non-detections in the X-rays, and that was a good ride. But then, lo and behold, it recovered and became basically the brightest AGN in the sky for about a year. And all of this is real variability up there. And as it began to re-brighten again, we saw this hard X-ray emission, the corona, kind of coming back on over time. And this is something we've never seen before. We don't know really what heats the corona in the first place. And so it was very exciting to see, the corona turning on in real time. So we interpreted this as a TDE that had some pre-existing AGN activity, where TDE comes, you have your corona and your accretion disk, your hot plasma, the corona, and the accretion disk in a normal AGN system. Perhaps this tidal disruption event comes in, disrupts your inner accretion flow, breaks up whatever magnetic field structure is powering this corona, and it destroys the corona. And what we're watching as we watch for several months later is that the corona is building up over time. So this is the model that we threw out there. And then we continued to monitor the source for a long time. So Megan started looking at these data at the beginning of her PhD, and what we found was that after this fading, it came back on, and it was the brightest AGN, as I said, in the sky, and it just parked at what is the Eddington limit for a 10 to the 6 solar mass black hole. And based on the stellar mass of the galaxy, we would expect the black hole mass to be about 10 to the 6 solar masses. So it really looked like it knows that the Eddington limit is there. And then as we watched this thing for several years, it faded down, and it really went back to what it looked like pre-outburst. That hard X-ray corona came back on, and it looked really normal. But we continued to monitor it just to see, because it was still pretty darn bright. And honestly, we were getting a little bored with the source, I would say. I was, it was fun, but how long can you keep on monitoring these things? But then we realized recently some more exciting, things were happening in this source. And this is what we found when we looked at the latest XMM observations. This is basically quasi-periodic oscillation in these light curves. So this is a several hour long light curves, and what we're seeing is quasi-periodic oscillations on timescales of 18 minutes to around 8 minutes. And this is the corresponding power spectrum, where you see it's very clearly peaked in the millihertz regime. And so this is many sigma. It's, each one of these is greater than 5 sigma results. It's definitely a real detection. So, what are these? I think that this source looks very similar to QPEs in some ways, whereas QPEs are these flares that happen every couple of hours and in some cases like every day. Here now we're seeing something that's on, millihertz frequencies or just a few minutes long. I think that there's evidence to suggest that these are related to QPE phenomena in that they are both associated with tidal disruption events. They don't look like typical AGN spectra. They don't show the corona, the hard X-ray emission. They're only very soft X-ray spectra. I didn't talk a lot about these, but they don't show any broad line region, no broad bomber lines pre-outburst, and they both show quasi-periodic behavior sometime after, several years after the original outburst. So I think we don't know what QPEs are. We don't know necessarily then what these millihertz, minutes long variability, quasi-periodic variability is. But I think that there's, compelling evidence to show that they are related and that whatever is explaining these QPEs, may be related to explaining these quasi-periodic oscillations too, because the sources, the systems are just so similar in other ways in their spectra. And so what we've been thinking a lot about is, how do we get thinking about, known disk instability models and known emery-based models. And for instance, if you had an emery-based model where your QPEs, hour-long systems, are explained by an orbiter that's on some kind of mildly elliptical orbit at like 100 gravitational radii, maybe this is like a more evolved system where your compact object or whatever has circularized. It's on much smaller, tighter orbit at 10 RG or less, and that's why you're seeing more like quasi-periodic, closer to circular orbits. And so, if that is indeed the case, I think it's a very exciting prospect that you'd have this orbiter on much, much smaller spatial scales. So we got really excited the first time we saw these observations. This is the first time that you see a QPO. There's like only 2 AGN that show QPOs, these like millihertz timescale QPOs. So this is the third. And this is the first time that we've seen the evolution of a QPO frequency over time. And we first got these observations here and in this third one here, and we got really excited that, oh my God, if this is an emery, and we're seeing this evolution of the QPO frequency, could it possibly be due to gravitational wave emission? And what we're going to watch is we can predict actually when we should see this thing fall past the event horizon, right? And we actually made a prediction that, okay, if based on these 2 data points, we didn't yet quite know about that one. We went back and found that one. But based off of these 2 data sets, we should expect that the merger should happen on February 24th, 2024. And it was like the nicest prediction I'd ever made. But then when we found it, actually, no, the QPO was still there. So not clearly gravitational wave driven, and it's decelerating. So it's like negative F double dot is parking at some frequency. And just to say, like, here is, the gravitational wave, predictions from the frequency evolution that you'd expect from gravitational waves alone. And you can see we're clearly not matching that. So we've been trying to cook up some ideas. Maybe we really have to go back to the drawing board with disk instability models. I think that we haven't ruled that out yet. None of them are immediately obvious. We can talk about reasons there. But if it is somehow related to an orbiter, you need it to somehow not be driven by gravitational waves, even when it's at 10, 5 gravitational radii. So one idea, one way that you might get around that is if your orbiter is a white dwarf, it has to be some kind of compact object because you're well within the tidal disruption radius for a normal star. But if you have, say, some low mass white dwarf system and you have mass transfer onto that white dwarf that can basically counteract the gravitational wave in spiral time and perhaps slow this thing down. So it's a bit of an you know, it's a big claim, and I think that would be amazing, but I think we need to basically keep monitoring this source and see if we can make predictions for such a model over time. But what is cool is that if, you know, this really is some kind of orbiter, it's in the millihertz frequency range, this source is at 80 megaparsecs, very nearby, and so it should produce you know, a strain large enough to detect this with LISA at an SNR of 7. Now, Chris tells me that that's a little bit low for blind searches of EMRI systems, but we know exactly where to look, and we know the frequency range that we should be looking for. It should match the X-ray frequency, so I think, you know, it's a promising prediction. So I would say I'll leave just with some exciting times ahead. You know, we're now at like 150 TDEs. Well, Ruben is supposed to see something like on the order of 1,000 TDEs per year. I'm also really excited. I'm a NASA participating scientist on the Ultrasat telescope. This is an Israeli space telescope to launch in 2027 with unprecedented, so basically 200 square degrees staring in the UV in a single band. So with like 5-minute UV cadence over a long baseline. And so for finding things like TDE and studying AGN variability, it'll be amazing. There's not many interlopers in the UV band, and so when you see one of these flares, you can be pretty confident that you're looking at a TDE. And then I think these QPEs are, you know, seen only in X-rays. When we have UV or optical emission concurrent, we don't see any flares. Again, another indication that this is something that's happening in the innermost regions. And what we've learned, if anything, from all of these QPE studies is that we have to look at our X-ray light curves. They show interesting things in them, and we need to follow these things up, even the very distant sources that Ruben will find. And so a mission like AXIS is a probe mission concept that would launch in 2032. I'm the deputy PI of that mission, and basically has, it's like super Chandra and super swift with fast slew capabilities. And so for following up these more distant objects and, you know, following them up over long baselines, something like AXIS is really what we need. So I'll finish it up there. Just to summarize, that, you know, these QPEs happening in tidal disruption events, I think, are a really exciting new window. And I hope that we can, you know, they're suggesting that they may be, you know, that compact objects may be common in galactic nuclei, and hopefully we can make some joint detections with LISA in the next decade. So thank you.